All right, clip number 2 on Chapter 11, Section 2, notes on areas of circles and sectors. In this clip, we're going to focus on kind of a classic geometric concept. As soon as we're introduced to shapes and how to solve for measurables with those shapes, we start interacting them together. That's kind of the natural progression of those math classes, those geometry classes. And in this case, since we're talking about area, we're going to start interacting some different area shapes together. And in this clip, I'm going to mostly just talk through this example that you see on your screen right here. You're going to get a couple of problems that actually deal with this exact type of dartboard in your Big Ideas assignment. So I'm going to kind of walk you through some strategies in this case. I'm not going to spend a lot of time solving things. You can look into the solution sheet that's uploaded into Google Classroom to see those things worked out. And I feel like I do a good job of kind of breaking those things down. So I encourage you to check that out. This one, I'm mostly just going to talk about the strategy into how to solve these and how to prepare your types of calculations here. And to also kind of point out maybe some things that you're far removed from for how to solve for areas of different kinds of geometric shapes. And then we'll do one more example that's on the second page of these notes that it kind of deals with a similar concept. But since we're dealing with areas in this section, the two-dimensional measurement of finding an area of a given shape, and most of this is about circles and stuff. And you see a few circles here drawn in this diagram. Again, what we're told here is that this is some complicated looking dartboard. And in this example, we're actually asked to find probabilities of hitting different regions in this dartboard. And so I just wanted to talk about these cases. Again, the general concept here is how to find areas of shapes that have different shapes interacting with it. It's really going to be the punchline. And what's ultimately going to break down to is just kind of getting creative and thinking outside the box about how to combine shapes together to find given areas. Because it's not exactly straightforward as to how to find, say, the area of just like the white corners in this small box on the interior. Okay, it's not exactly like just like plain as day as to how to find the area of those things. It will involve some interaction between different shapes, whether I'm adding areas together between different shapes or subtracting things from other shapes. So I'm going to talk about that in this clip. Okay, before I do, this particular set of examples, and again, this is reflected in some of your problems in your Big Ideas assignment, you're going to be asked to find the probability of hitting a section of the dartboard. And so just a little background on probability. This is a unit that we did at the end of first semester, but I want to just kind of break down what probability is again. I have it here in the margin. Fundamentally, probability is some percentage, basically a likelihood that something will occur. Okay, so when I'm talking about throwing a dart at this dartboard, we're going to assume that me throwing a dart at this dartboard has there are no outside factors that are going to affect probability one way or the other, how accurate I am or not. Okay, I'm simply throwing a dartboard here, and we're looking at the probability of hitting different sections based on these questions. And so what that means from a probability measurement standpoint is we're going to be talking about the likelihood in terms of a decimal between 0 and 1, or describing it as a percentage, which is simply converting that decimal into a percentage that will be between 0 and 100%. 100% likelihood, meaning that no matter what happens, it will be a success. 0% meaning no matter what happens, it will be a failed attempt. And then like the various numbers in between, like a 50% chance would be I'm just as likely to succeed as I am to fail, that sort of thing. So how is probability measured? It's given by this ratio right here. It's measured by the number of successful attempts. So in the case of throwing something at the dartboard, the likelihood that I hit a given region that I'm aiming for, versus in the denominator, the total number of possible outcomes, which in this case will be the area of the entire dartboard. Okay, me just hitting it. Okay, so how will I go about measuring this? So let me break down this question, and we'll just look at question A right now. I'll talk about the differences for B and C because some of the language there is a little bit different. But it says that we throw a dart at this given dartboard. It's not a regular looking dartboard. It's a crazy looking thing right here. And our job is to find the probability that our dart lands in an indicated region. So for part A, if I'm asked to find the probability that I throw a dart at this dartboard and I hit one of the blue regions, first thing to do would be identify where everything that blue is, okay? And it's only in these corners, okay? And it may be tempting to just treat each of these corners like a triangle. because they're kind of triangular in shape. But the problem here is that this is a curve. Quite obviously, this yellow circle forces this section here to be curved, meaning that this is not just a simple triangle. It is a kind of curved portion of a triangle in that corner. And there are also these four corners to deal with. So the long way about doing this, the inaccurate way about doing this, would be to try and find the area of each of these little sections one by one. But here's where I'm just going to kind of show you the strategies as to how to find the areas of these irregular shapes. Because if I look at just each of these corners by themselves, it's an irregular shape. It's not a nice geometric polygonal type of shape where they're nice straight edges and stuff like that. Instead, I'm dealing with curved sections that's probably a little bit more normal to real life. But because each of these geometric shapes that are shown in this dartboard are regular geometric shapes, I can treat them as such. So here's the strategy. I'll just kind of jump to it. So the blue sections here. The simple strategy here would be to treat this as, well, the entire dartboard, this blue box, is a 6-unit tall by 6-unit wide box. So I can find the area of that box. In this case, that would be 6 times 6, or 36 square units for the entire dartboard, which those blue corners are part of. But if I only want the blue corners, I'm going to subtract out the stuff that I don't care about, namely this yellow circle and these green triangles, this white box, the red bullseye circle here in the middle. But I don't need to subtract out each of those spaces individually. I can just treat this as that yellow circle and this entire contraption here in the middle are all just not blue. So from a geometric standpoint, to solve this, I would simply take the area of the whole square and then subtract out the yellow circle. That will leave me with just each of the blue corners. So from the area standpoint here, again, the box is simple enough, 6 units by 6 units. For the area of the circle, I got to be a little more careful here. Technically, this has a 6-unit diameter for the circle, as shown here, it fits perfectly in this 6 by 6 box. So if I wanted to find the area of that circle, well, that just happens to be the subject of this section. Area equals pi times r squared, but I need the r. Well, if the diameter is 6, cut that in half. That tells me that it's a 3-unit radius. I could do pi times 3 units squared to find the area of that yellow circle, which would be 9 pi. Subtract that from the 36 square units of the entire box, and that gives me the area of the successful attempts, the area of just the blue section. Okay. And I need that area of just the blue section, and I'm going to divide it by the area of the entire box, the entire dartboard, circle included, which would be 36. So my result here for part A should be 36 minus 9 pi, all divided by 36. That will give me a decimal, which would give me the probability in decimal form. If they want it in percentage form, I simply move that decimal 2 spots to the right, and that converts it into a percentage. Again, you can see that fully worked out in the solution sheet. I'm not going to spend a lot of time beyond just discussing it right there. But just to make a couple of extra points here about B and C, for strategic standpoint, find the probability of either yellow or green. That means I can hit either yellow or green, and I have succeeded. So as far as the numerator to that probability here for part B, I'm going to be considering the fact that I can hit either the yellow circle or the green triangles. What's not included in there, I cannot hit the red bullseye. I cannot hit this little white box around it. I cannot hit these blue corners on the sides. So from an area standpoint for this, I would find the area of the yellow circle and just subtract out the white box. Why don't I need to bother adding in the green triangles? Well, the green triangles are inside of the yellow circle. So if I hit here or here, I'm still inside the circle. So I'm still just finding the area of the circle. Why wouldn't I have to subtract out both the white box and the red bullseye? Well, because the red bullseye is completely contained in the white box. So as long as I've deleted the white box, that includes the red bullseye. So for my numerator here, I'd simply find the area of the yellow circle, which happened to be 9 pi, as found in part A, and then subtract out the area of this white box, which is a 2 unit by 2 unit box. So I'd subtract 4 square units from that. That would be my numerator. The denominator for both B and C will both be the same as A, because the total possible outcomes for all three of these guys is just the whole dartboard, 6 by 6. For part C, just again discuss this, the probability of me hitting something just not yellow. Okay, so I can't hit any of the yellow region. That also implies that I can then hit any other color. So I can hit those blue corners again, and I can find the area just as I did in part A. Take the area of the whole box and subtract out the area of the circle. So that will tell me the probability of hitting each of the blue spots. But I could also hit the green triangles, the red bullseye, or anything in that little white box right there, and still be within, still be not yellow. And so in that case, I would just add in the areas of each of the triangles. Just to remind you, the area of each of these respective triangles would be 1/2 base times height. So the base here would be 2 units long. The height seems to be 2 units long as well. So 1/2 2 times 2 for each of the green triangles. And then the red bullseye is part of the white box. As long as I hit anything in there, I'm still just not yellow. So I do 2 by 2, another 4 square units that I can hit. So I'd add up the 2 green triangles, the area of the white box, and then add in the answer from part A for the blue corners. And that would be everything not yellow. Add all that stuff together, divide it by the area of the total dartboard, and that will, again, give me some probability, some percentage. Again, I'll emphasize that each of these is completely worked out and explained and kind of redrawn for what respective areas we can or cannot hit in the solution sheet. I'll redirect you there in Google Classroom to look for that. Okay, for the last example I want to talk through in this clip, I'm actually going to flip the page to the second page of notes. It's a similar type of problem, so I just want to talk our way through it. It's this guy right here. And it's a similar concept. Okay, we're given this shape. And here's our situation in this case. We're given a rectangular wall. So it's rectangular because it has this 10 plus 16 foot height and a 36 foot length. And then it has this missing section, this archway, call it an entryway into some other room or whatever it might be, that has in turn a 16-foot height from here to here, and then this semicircular archway, this curve right there, that's missing from that wall. And the situation we're given here is that we're painting this wall, and we need to figure out how much square foot of paint we need to cover. So basically, it's a long-winded way of saying find the area of this shaded region. So essentially, this is a very similar problem to what that dartboard problem is. In this case, we're finding the area of irregular shapes. So in this case, the way I would attack this strategically is to find the area of just the basic rectangle here. This is 10 plus 16 or 26 foot tall, 36 foot wide. Simple multiplication of 26 times 36 will give me the area of a straight rectangle here. But then I would subtract out this archway. And this archway can kind of be broken up into 2 pieces. Right here, this is a simple 16 by 16 square, okay, as shown by this little division right here. 16 foot up to that point, 16 foot wide. I can find the area of just that square, 16 times 16. And then I would subtract that from my 26 by 36. And then I need to subtract out this little semicircle archway. And that semicircle description tells me how I can solve for that area. So this 16 feet across right here for this semicircle, what I can do here is I can find the radius of that semicircle simply by cutting that in half. If it's 16 feet across, that's a diameter. So 8 feet would be the radius of this semicircle. And if I want to find the area of the semicircle, well, just like we talked about at the beginning of these notes, the area of a full circle is pi times r squared. I now know r is 8 feet. But that would be a full circle if it completed all the way around. I've already subtracted out the bottom part of this circle, so I just need to do half a circle. So I just do pi times r squared and then cut it in half. That's the area of that semicircle arch. So the radius again would be 8 feet here. Square it, that's 64. 64 times pi would give me a full circle, but I only need the semicircle, so 64 pi divided by 2 would give me the area of that semicircle. I'd again subtract that from the 36 by 26 foot total rectangle.